Welcome to Study Loop.
So if we want to try to figure out what levels of nitrogen and phosphorus are going to maximize our yield equation, we're first going to need to take the derivative of this with respect to x and y, set that equal to 0, get these a and b points, and then just plug it into our second partial derivative test that they give us in the book, and then just see which of these categories it falls into. So let's go ahead and find our partials. So I'll do the partial with respect to n first. So we have n times e to the negative np, or negative n minus p. So we're going to have to use product rule. So remember, this k and p are constants, so we can pull those out front. So it'd be k p, or actually let me write this is y sub n. And this is, so I'll pull that out first, so kp, and then we have del by del n of n e to the negative p, or negative n minus p. So again, product rules would be kp times, well, derivative of n is just 1, so it'd be e to the negative n minus p, and then plus n times, and the derivative e to the anything is first itself, and then we take the derivative on the n side. So that is just going to be negative 1. And now we can go ahead and factor out this e. So it would be k p e to the negative n minus p, and then it would be 1 minus n. Okay, so if we're trying to find what values maximize this, first we're going to set this equal to 0. So the only things that are going to be variables in this case is p and 1 minus n. So that's going to imply either p is 0 or 1 minus n is 0, so n is going to be 1. So we have that. Now let's go ahead and repeat this for the other derivative. So let's take the partial of this with respect to p. And actually notice how this is symmetric in the sense of if we were to switch all the n's and p's around, we would get the exact same equation. So if we come over here and just switch all the variables around, we should end up with the exact same derivative as well. So this is going to be y sub p, and this is going to be equal to, so it'd be k n e to the negative n minus p, and then 1 minus p if we just switch the variables from up here. And if you just take the derivative like normal, you'll see we get the same thing. But I will just kind of skip a little bit to make our work a little bit easier. So now we're going to go ahead and solve for this. So this implies that, so let's see. Oh yeah, either n is 0 or 1 minus p is 0, which that gives us p is equal to 1. Right. Now, if we're trying to find what value to maximize this, we can actually go ahead and throw a couple of these out just by looking at this. So notice that n cannot be 0, nor can p be equal to 0. Because if these are equal to 0, we just get 0 for both of those. So that is going to imply that n has to be 1 and p has to be equal to 1. Because again, if we use n is equal to 0, p is equal to 0, we have 0 times something. So I'll just kind of write that because 0, 0 is equal to 0, and that's not going to be a maximum value. Okay. So now we would just go ahead, take this, plug it into here, and that should actually give us our max. So let's see what we get. So y11 is going to be, so it'll just be k 1 times 1 e to the negative 1 minus 1, which would be 2, or not 2, just k times e to the negative 2, or you could just have k over e squared. So this is where our max is. So this is the max yield, and that is going to be when n is equal to 1 and p is equal to 1. And I guess we could really just stop here if we wanted, because we really don't have anything else to check. But just to make sure that this is a maximum, we should follow through with these steps over here. So again, I mean, if you are just content with what we were doing here, you could just go ahead and say the maximum yield is at n is equal to 1, p is equal to 1. But let's actually see if we can confirm that this will be a max. So let me come up here. Where's the derivative? Here it is. So this is supposed to be yn. So yn, and then yp is this here. Okay. Now, if we were to go ahead and bring this down here to see what we need. So we need all of our second partial derivatives. So let's go ahead and find those. So if we were to just do the partial of this with respect to n, so we get the second with respect to n, and again we're going to have to use product rule. Kp are just constants, so it would be Kp times, well, the derivative of this, actually I'll do the derivative of this first, so that's just going to be -1, so it would be -1 e to the negative n minus p, and then minus, or plus the derivative of that. I was getting a little ahead of myself. So it'd be 1 minus n, and then e to the negative n minus p, and then the derivative of this is going to be -1. Then again, we can go ahead and factor that out. So that is going to be kp e to the negative n minus p, and then it would be -1 minus 1 plus n, so it would be kp e to the negative n minus p, -2 plus n. So actually I'll write that as n minus 2. Okay. And again, notice how this and this are symmetric. So if I were to just take the derivative of this with respect to p, I should just get this, but where p and n are all flipped. So I'll just kind of be a little bit lazy, but you could go ahead and redo this again. You'll see that we do get the same thing as what I'm about to write. So this p becomes an n, e to the negative n minus p, and then p minus 2. All right. Now that just saves us a little bit of time. And lastly, what we're going to want to do now is go ahead and find our mixed partial. So I'll just take this and take the derivative of that with respect to n. So del by del n. So now this 1 minus p is a constant as well as the k, so yn p is going to be k1 minus p, and then del by del n of ne to the negative p minus p. And that should give us, so it would be 1, so e to the negative n minus p, and then plus n e to the negative n minus p times negative 1. So again, factor that out, and that would give us k1 minus p, and then e to the negative n minus p, 1 minus n. Okay, so that's our mixed partial. And now we just need to plug in 1, 1 into all of these, and then we can plug everything into that equation up there. So let's do that. So let me slow this down a little bit. So if we do 1, 1, then this is going to become, it looks like k e to the negative 2, and then that is just going to be negative 1. And then over here, if we do this, that is going to be k times 1, so then e to the negative 2, and then times negative 1 again. And then over here, if we plug in 1, 1, that should give us, actually, maybe I should write it a little bit more exact. So this would be yn of 1, 1. And then over here, this is going to be ypp of 1, 1. These are equal. And then over here, this would be ynp of 1, 1. And if we plug those in, well, 1 minus p is 0, so that's just 0. Okay. Now, let's see what that equation was again. So we multiply them together and then subtract off the mixed partial when we square it. So this is going to give us d is equal to, so it'd be negative ke to the negative second times negative ke to the negative second, and then minus 0 squared. So these cancel out, and then we would just get k squared, and then e to the negative 2 times e to the negative 2 is e to the negative 4, which would be e to the 4th. So this is strictly larger than 0, which means we fall into either case A or B. And then it says we need to check one of the mixed partials to see if it is positive or negative. So over here, if we check ypp at 1, 1, this is going to be negative k over e squared, which is less than 0. So then notice that this is going to be case B. So then that this implies 1, 1 is max. So I guess we really didn't need to do all of this, but it does kind of help confirm that for a nitrogen level of 1, whatever that means in a phosphorus level of 1, then we get our max value. Because a lot of times we might do this and then end up getting like a minimum or a saddle point, or the test is just inconclusive. So it never hurts to kind of double check our work.